canonical ensemble. So in the previous lecture, we explained you that a more general ensemble will be when you have not fixed only the temperature or the average of the energy, but also you know the information about the average of the number of the particles. So if you fix it, or if you have the data about the average of the number of the particles, so you can define that as a more general ensemble, call it grand canonical. So the only things in the grand canonical ensemble was that a new concept of the chemical potential, so, and a new parameter, we call it fugacity, so, which is a function of the chemical potential. So this is the chemical potential. And we explained that actually by simple methods. We find that the key function here is d, this is called the grand canonical partition function, and this is a logarithm of the lowercase q, and this is actually a sigma of the r s minus theta e r minus alpha n s. And we talked about what is the alpha and what is the beta, so that's. So this ER will be the total energy, and this is NS will be the total energy for the given number. I want to tell you that we have two types of the system as we explained it, the localized system. So localized system, the one which the Hamiltonian has the potential, like harmonic oscillator, solids. So solids or the metals are categorized as localized system in quantum mechanics, in many body particle, and in statistical physics. They normally have the Hamiltonian with the harmonic oscillator potential terms. So the Hamiltonian is normally a kinetic term. Okay, if you consider non-relativistic, you can write p squared or 2m plus a term which is called the harmonic oscillator term. Of course, it can be continued by some anharmonic terms, and there is no any way to consider the statistical physics when you have the anharmonic term, except the perturbation theory. So you can have it the perturbative term, perturbative. I mean the anharmonic terms, consider it as a small corrections, tiny corrections with respect to the original potential. So in this case, you can consider the statistical physics for that. But if the harmonic oscillator terms, anharmonic terms, you know what is that, like alpha, q, beta, and these things. If this term becomes higher, so and larger than the original harmonic oscillator potential, so there is no any way to consider the statistical physics for that, except that some approximation techniques you can apply. And there is another thing, and for that, we learned that in the, you remember in the canonical picture, we learned that the harmonic, the partition function for n particle of these things will be just q1n. And for non-localized, like free particle, not free, exactly free particle, it can be relativistic or non-relativistic. For example, the Hamiltonian of this, it's given, it's defined as a free particle, in classical mechanics and in quantum mechanics also. You can add the quadratic terms or something else and make it this non-relativistic, relativistic. This is a relativistic correction. When the momentum of the particle is so huge, so relativistic correction should be added to the original non-relativistic. And that's very important because, you know, the molecules Not molecules, but the particle can have the relativistic behavior as well as the non-relativistic one.
Is it like the well potential, infinite well potential?
What?
The non-localized example for non.
When you have a potential, it will be considered localized, and when you
for the infinite well.
Any potential. I write a harmonic oscillator because harmonic oscillator is useful to make a model for the solid state. You can have any other potential. So just by potential. So if you have a potential here, so it will be categorized as a localized. It means that the oscillation or the motion is happening near the equilibrium point of the system. And for equilibrium point, to have the equilibrium point, you need to have the potential. So
even if the potential was zero?
If potential is zero, it's free particle. So, and here we learned that the Qn will be Q1n over n factorial, and that was the correction we needed to have the additive entropy and to avoid the problem like the Gibbs paradox and these things like that. So, to additivity the potential. So, I want to see that what will be the effect of this local and non-local over the grand canonical and so on. So, by the method which I don't write it that because a lot of detail and we will spend not enough time. We don't have enough time to do that. Time means that it's not necessary. At the first reading of this book, you don't need it to know that. So you can show that there is a first reading of any textbook and there is a second reading and there is an end reading of this book. At the first reading, you don't need it to read out. You need to just understand a little bit about statistical physics. Second reading, you can find more information. So D will be, for localized particles, it will be sigma m and for non-localized, you understand what happened at here. The things which happen here is that we have a ZE power beta mu. Yeah? And you remember what was the alpha? Alpha was minus mu over KT, so minus mu beta. Huh? Just by combining these together, you can show that E minus alpha NS will be E mu beta NS. And you can write it this E mu beta power NS. And this will be Z power NS. And you have a double sigma here, over R and over S. It means over N. Yeah. Over the energy state and over the numbers of the state. So you can make it this 2 sigma. So actually you can keep it this NS inside the sigma. And say that the sigma in SS is we call it N. We separate the part of the sigma S and keep it the sigma R, and sigma R will be over the old energy. So you will see that this will be the original partition function, the normal partition function. These two equations are the main grand canonical partition function for the system of localized. But we can make it this more simplified. You can make it more simplified that. How you can do that? So the sigma is start from the 0, so there is a problem about the convergence of this series. Who know that this will be less than 1 to have the convergence? You know, in the mathematics, to have the xn, n from 0 to infinity, this is 1 over 1 over x, if and only if the absolute of the x is less than 1, huh? Only. You have this here, exactly this here. So the partition function for localized z and beta and n, z and beta will be sigma n 0 to infinity z e, not e, q1 beta power n. And this is like xn, so if and only if the absolute of zq beta less. The problem of convergence here is still important because we don't know that the absolute value of this will be less than 1 or not. But anyway, we suppose that it will be satisfied by some requirement. And for non-localized, you just you have to be still a little bit flexible with this expression. So I write this expression of non-localized in the following form. So if you write that, you see that not only that, you have a basic mathematical expression, this exponential x, sigma x n. So this is x, huh? So it will be sigma n exponential x exponential zq1 and beta. Okay. Remember that these are not the same, huh? This is for the harmonic oscillator, for example, and this is for the free particle like gas. They have the same symbol, but they are completely different. This is the partition function for localized, and this is for non. Immediately, you know we have something called we have a different system which are considered very important actually. One thing is, okay, the single particle partition function is also, I needed to find this. I mean make it this more simplified, this Q1. This Q1, what is that? The Q1 beta is 1 over h cubic integral dq dp e minus beta h q and p. This is a single particle harmony, a single particle partition function in the canonical ensemble. So this is a general partition function of a single particle. If you have a non-localized case, in the non-localized case, let's me to see what happened. You have a potential here, potential will be seated with this, and you have a kinetic term. Kinetic term will be seated with that. Yeah? So each integral you can evaluate it. So this integral, you know that how to calculate dA e minus beta p squared plus 2m. This is just cubic of integral of the dA x minus beta ax squared over 2m. Minus infinity to infinity. And this integral, you know what is that? Poisson integral, radical 2mp over beta cubic. This term. And this time we don't know what is that, but you see that it will be function of beta only, huh? Only function of beta. Yes? So Q1 beta will be 2pm h beta multiply to the integral of that. This integral we call it f a t, okay? Because it's function only of the t, no? Or beta. So I call it this f a t. F a t is the integral of dq e minus beta vq. And you know that the beta is 1 over kBt. Anyway. And you know that these are just I want to write a kBt also, kBt 3 over 2 f a t.
Is it 1 over 3 or power 3? 2 and 5.
2mp over beta. And beta is 1 over kBt. So this is, look, this is called C f a t. C is the constant of the PM and these things.
It is square root of 2m pi over h to power 3.
Yes. Can make it this more simplified or something more effective, but anyway. This is like t power 3 over 2 f a t. And f a t is this. This is called form factor or something like that in quantum mechanics and in the solid state. So let me go back and finally write the grand partition function for non-localized case. So even it's very common that to set this 1 h over 3 with this integral and define that, like, is better to do that, With that, you don't need it this here, no? It will be more beautiful. You can keep it this here, how you want, So for non-localized, so we continue, so we can write the grand partition function. D will be 1 over z q1. Q1 is t over 3 over 2 f a t. You need to be careful about writing the f a t. So f a t is a collective things like all of them. C also, you can put it as C. C is this constant of radical distance. For localized, what we are talking about, we have a potential here, no? Sorry, potential is localized case. Why you didn't mention that? Potential is localized. So for localized, we find the partition function. For non-localized, For non-localized, you don't have the potential, huh? You don't have the potential. So the partition functions Q1 will be just this. There is no potential. This integral is volume. So can you calculate this integral? Yes, we calculated that before.